Today's episode is titled, Kiwifruit Can Kill You Unless. Dramatic, yes. Misleading, also yes. But hey, if I titled it Fruit Enzymes and Protein Hydrolysis in Culinary Applications, you'd already be asleep. This fuzzy little fruit may look innocent, but inside, it's packing biochemical weapons. Weapons that can dissolve flesh, and we eat it voluntarily. Stick around, because in this video, we're diving into the wild chemistry behind how fruits like kiwi and pineapple literally digest meat. You'll learn how your body fights back against these enzymes like a biochemical ninja. And by the end, you'll know exactly how to master the art of meat tenderization without turning your steak into soup. Plus, you'll finally understand why canned pineapple is the culinary equivalent of a retired superhero. Let's get juicy.
When you marinate meat with kiwi, pineapple, or papaya, something magical happens. The meat becomes tender, juicy, and easier to chew. Why? Because these fruits contain enzymes, like bromelain in pineapple and actinidin in kiwi, that break down proteins. These enzymes are proteases. They slice up proteins like a ninja chef with a vendetta against collagen. Let's break it down. The enzyme binds to the protein in the meat. Then, using water, it cleaves peptide bonds, the chemical links between amino acids. The result? Smaller, softer protein fragments. It's called proteolysis, and it's basically molecular butchery. Translation? Enzyme meets meat, meat gets chopped, dinner gets delicious.
The rate at which fruit enzymes tenderize meat is highly dependent on temperature. The relationship is characterized by three key zones. 1. Cold temperature, refrigeration, about 0 to 10 degrees Celsius. The enzyme molecules have low kinetic energy and move slowly, resulting in fewer collisions with the protein substrate. The reaction is very slow. This is why you can leave a marinade in the fridge for several hours without the meat turning to mush. However, some tenderization does occur. 2. Optimal temperature, about 40 to 65 degrees Celsius. Enzymes achieve their highest rate of totalysis. The reaction is fastest. This high activity explains why these enzymes continue to tenderize the meat for the first few minutes of cooking before the temperature gets too high. 3. High temperature, above 70 degrees Celsius. When the temperature rises too high, the enzyme's three-dimensional protein structure, conformation, begins to break down. This process is called denaturation. Tenderization stops because the enzyme's active site is destroyed, rendering it incapable of binding to and cleaving the peptide bonds. This is why canned pineapple is not an effective tenderizer. The heat of the canning process denatures the bromelain.
The fundamental reason enzymes are such effective tenderizers lies in their ability to manipulate activation energy, EA. What is activation energy? Activation energy, EA, is the minimum amount of energy required for a chemical reaction, like the breakdown of a protein, to start and proceed spontaneously. In the case of meat, the tough peptide bonds in collagen and muscle fibers have a high EA and require a lot of energy or extreme conditions like concentrated acid to break naturally. How the enzyme works? Enzymes, as biological catalysts, speed up the reaction by significantly lowering the activation energy barrier. The enzyme, E, binds to the substrate, S, at the active site and puts strain on the peptide bond. This binding and distortion stabilize the high-energy intermediate, called the transition state. By stabilizing this state, the enzyme essentially provides an alternate, lower-energy path for the reaction to occur. This means fewer random, energy-rich collisions are needed for the bond to break. The dramatic reduction in activation energy is what allows the meat to be tenderized in a kitchen environment, near room temperature or warm cooking temperatures in minutes or hours, rather than geological time. For the enzyme reaction proteolysis to occur on its own, namely spontaneously, the overall process must be thermodynamically favorable, which is determined by the change in Gibbs free energy, delta G.
The breakdown of large protein molecules, like collagen and muscle fibers, into smaller peptides and amino acids is a specific type of chemical reaction called hydrolysis. Enthalpy change, delta H, measures the heat absorbed or released during a reaction. When a peptide bond is broken during proteolysis, the enthalpy change is actually slightly positive. Typical values fall around plus 10 to plus 20 kilojoules per mole, meaning energy must be absorbed to break the amide bond. This endothermic nature reflects how strong and stable peptide bonds are. Entropy change, delta S, measures the change in the degree of disorder or randomness. The proteolysis reaction takes one large, highly ordered protein molecule and cleaves it into multiple smaller, independent molecules, peptides and amino acids. Having many small, moving product molecules instead of one large, rigid reactant molecule significantly increases the disorder of the system. A positive delta S, increased disorder, contributes favorably to spontaneity. Delta H can be slightly positive or slightly negative depending on protonation state, but the entropy change, delta S, is strongly positive. With representative experimental theoretical numbers, delta S is approximately plus 80 to 85 joules per mole per Kelvin. The Gibbs free energy, delta G, combines enthalpy and entropy changes to determine if a reaction is favorable at a given temperature T, using the equation delta G equals delta H minus T delta S. For a reaction to be spontaneous or favorable, the delta G must be negative. When you combine enthalpy and entropy terms in the above equation, the entropy term dominates, making proteolysis spontaneous under physiological conditions. So even though bond breaking costs energy, the increase in molecular freedom drives the reaction forward. Since the reaction is highly favorable, why doesn't meat just spontaneously fall apart at room temperature? Kinetics versus thermodynamics. While the reaction is thermodynamically favorable, that is, delta G is less than 0, it is kinetically slow. This means the activation energy is very high, acting as a massive barrier. The enzyme's function, it does not change the delta G of the reaction, it only works to drastically lower the EA barrier, allowing the inevitable and spontaneous breakdown of the peptide bonds to occur at a rapid, useful rate. Chemical kinetics relates the reaction rate constant K to the activation energy EA and absolute temperature T through the equation K is proportional to E to the minus EA over RT, where R is the gas constant. It shows that a lower activation energy at a given temperature leads to a significantly higher rate constant and thus a faster reaction rate. While these enzymes are powerful protein-digesting molecules, your body has several layers of defense to protect its own proteins from being broken down. 1. Stomach acid. The first and primary line of defense is the highly acidic environment of the stomach. Most enzymes have optimal pH ranges for activity, around pH 3 to 7. The stomach's gastric juice, with a pH typically between 1.5 and 3.5, can denature, unfold, and deactivate a portion of the enzyme, greatly reducing its power. 2. Digestive proteases. Enzymes like pepsin and trypsin break down dietary protein, and these also target and inactivate foreign enzymes. These human enzymes are highly effective at breaking down the enzyme protein itself, essentially digesting the digestive enzyme. 3. Mucus lining. A protective mucus, which is a complex mixture of glycoproteins, protects your gut walls. 4. Protease inhibitors in your blood trap any rogue enzymes that sneak through.
In summary, while a dietary enzyme is an effective tenderizer, your body is well equipped to neutralize it using acid denaturation, self-digestion by its own enzymes, and physical and chemical inhibition by protective proteins in the gut and bloodstream. In short, your body is like a biochemical fortress. Fruit enzymes may be tough, but your gut is tougher.
So there you have it. Kiwi fruit isn't just a snack, it's a biochemical scalpel. We've sliced through enzymes, dodged digestive destruction, and even flirted with thermodynamics. All in the name of tender meat. If you learned something new, laughed at least once, or now fear your fruit bowl just a little bit more, hit that like button. Subscribe for more science that sneaks into your kitchen, your bloodstream, and occasionally your nightmares. Remember, your body is a fortress, your steak is a battlefield, and your fruit, a delicious little saboteur.